So let's first invite Dr. Kai-Chen to bring us an overview of OpenMMLab and its recent updates. Dr. Kai-Chen is currently a young scientist at Shanghai AI Lab, leading the OpenMMLab team. He received his PhD degree from the Chinese University of Hong Kong. He has published more than 30 papers on top-tier conferences and journals in computer vision, receiving more than 7,000 citations. So,
hello, everyone. I'm Kai-Chen from Shanghai AI Lab, and also the lead of OpenMLab. Today, I will talk about OpenMLab, a foundational platform for computer vision research and production. With the development of deep learning and computer vision, big companies and research institutes open source deep learning frameworks such as Caffe, TensorFlow, and PyTorch. Of course, today, PyTorch has almost dominated the AI research community. With these frameworks, the cost of conducting research and implementing algorithms greatly decreases. More researchers tend to release the code when paper get published. On top of PyTorch, we hope to push one step forward from a unified deep learning framework to a unified algorithm framework. So we announced the OpenMLab project in 2018. OpenMLab is an open source computer vision algorithm platform with a unified architecture for training and evaluation. It covers more than 30 research areas, implementing over 300 algorithms, including classic and state-of-the-art ones. We also released more than 2,000 pre-trained models and built fair benchmarks with standard training settings. We hope these models can provide a solid foundation to researchers. OpenMLab was first released in 2018. At that time, there are only two packages, MMCV and MMDetection. In the next year, 4 new code bases were developed. In 2020, we supported more mainstream tasks such as classification, segmentation, 3D object detection, etc. During the past 2 years, we kept open sourcing toolboxes for new areas and closely collaborate with colleges and research institutes to work on more directions. In the future, we will extend OpenMLab to multimodality learning and language models, and more new projects are coming. Today, we have built a powerful framework based on PyTorch. We developed 2 foundational libraries for computer vision, MMCV and MMEngine. MMCV implements lots of network operators that are missing in PyTorch. These operators are supported on both CPU and GPU. It also implements common data augmentations and image processing functions. MMEngine provides a generic and universal training engine, serving as a foundation of all algorithm code bases. Based on MMCV and MMEngine, we construct code bases for different research areas, like MMPretrain, MMDetection, MMSegmentation for image perception, MMTracking and MMAction2 for video understanding, MMagic for image and video editing and generation. These code bases involve most mainstream research areas in computer vision. Towards industrial applications, we developed MMDeploy for model deployment. It bridges the gap from research to production. OpenMLab has gained great community impact these years. It has received 80,000 stars on GitHub. It is noted that OpenMLab is not a competitor of PyTorch. Instead, it is part of the PyTorch ecosystem. We just show this figure as a reference. More importantly, there are more than 1,000 contributors from over 40 countries. These contributors actively commit code to OpenMLab projects and make it stronger. In the academic community, OpenMLab projects have been adopted by over 2,000 papers, including many high-impact ones, such as Swing Transformer. One of the advantages of OpenMLab is that it provides high-quality implementations for different areas, making it a good benchmark when researchers want to evaluate their models on downstream tasks. Meanwhile, we have seen more than 20 challenge winners adopting OpenMMLab as their codebase. Next, I will briefly introduce some codebases in OpenMMLab. The first one is MMDetection. It is perhaps one of the most well-known computer vision libraries. It supports instance-level recognition tasks such as object detection, instance segmentation, and panoptic segmentation. In later sessions, other speakers will talk more about it. MMPretrain originates from MM classification and MM self-soup, aiming to provide a unified codebase for pre-training. It supports various vision backbones and vision language models, as well as self-supervised learning methods. It is also compatible with other codebases of OpenMMLab and makes it easy to integrate pre-trained models in downstream tasks. And the next is MMSegmentation. MMSegmentation is the most widely adopted semantic segmentation toolbox in recent years. It can be applied to general scene understanding, self-driving, remote sensing, and medical imaging analysis. It incorporates over 30 algorithms and releases more than 400 models. With lots of application studies, we provide a standard benchmark with fair comparison. MMDetection 3D is a platform for general 3D perception. It supports 3D object detection methods with different sensors like camera and LiDAR. Since it adopts a similar design to MMDetection, it is much easier to integrate 2D detectors and use modules from MMDetection. MMRotate extends MMDetection to implement rotated object detection, which are useful in remote sensing or text detection. Here is a demo. Okay. MMOCR is a toolkit for text detection, text recognition, and the corresponding downstream tasks, including key information extraction. It supports a variety of state-of-the-art models and provides a comprehensive set of utilities, which can help users assess the performance of models. MMPose is a pose estimation toolbox. It contains a rich set of algorithms for 2D multi-person pose estimation, hand pose estimation, face landmark detection, whole body human pose estimation, fashion landmark detection, and animal pose estimation, as well as related components and modules. Here is an introduction video of MMPose and its applications. We can see that it supports 2D human pose estimation of multi-person, and also 133 key points, and 3D human pose. And here is also 3D human pose with mesh representations, and also 3D hand pose. And also the animal pose estimation. And there are more related pose estimation tasks. And we can build interesting demos and applications based on MMPose. So this is our webcam demo. You can try it with our code base. Okay. Next one is MMAction 2. It implements various algorithms for video understanding tasks, including action recognition, action localization, spatial temporal action detection, and skeleton-based action detection. We support over 20 different algorithms and 20 different datasets for these tasks. And also MMagic. MMagic originates from MM editing and MM generation. It unlocks the magic of generative AI. MMagic is a powerful toolbox that supports low-level algorithms based on both CNN, GANs, or different diffusion models. MMagic supports popular applications on image restoration, text-to-image, 3D-aware generation, in-painting, matting, super resolution, etc. Here I will show a video. So with MMagic, we can do the text-to-image generation and the 3D-aware generation, and also many image restoration tasks, and also video super resolution. And here is a video interpolation. We can use a 30 FPS video to make a 201, and also lots of GANs. And the image restoration and super resolution. Okay, now, besides developing toolboxes for research, we step forward to production. So next section, I will introduce OpenMMLab from research to production. So from research to production, what we need to do is to deploy the model on specific devices, such as CPU, GPU, or mobile phones. When we have developed a novel algorithm and obtained a PyTorch model after training, a general pipeline for model deployment is to first, we convert it to some intermediate representations, namely IR. For example, Onyx. Then we convert it to the format allowed by the inference engine on the target device. During this process, we need to resolve some issues such as how to convert the model, how to implement the operators that are not supported by the IR or the inference engine. Now we present the architecture of MMDeploy. MMDeploy naturally supports OpenMMLab projects like MMPretrain, MMDeploy, MMSeg, etc. It mainly consists of 3 components: model converter, SDK, and backend extension operators. The model converter converts PyTorch models to IR models, and then IR models to inference engines. SDK provides simple and unified APIs to execute the model. And users can develop applications based on the SDK. We implement lots of operators on different backbones and devices. There are 4 major advantages of MMDeploy. Firstly, as an open framework, it supports various inference engines such as TensorRT, Onyx Runtime, LibTouch, etc. And it is compatible with multiple platforms, including Linux, Windows, Android, and macOS. Besides, MMDeploy allows users to develop with different languages and can be flexibly integrated to the production system as required. For example, you can just use the IR model or inference engine models, or you can also integrate the whole SDK to your application. Here is an example of how to use MMDeploy to deploy RetinaNet to NVIDIA GPUs. The first step is to run a single deploy script to convert the PyTorch model to a TensorRT model. Then we can obtain a result. We can obtain a result folder with the binary files and config files. Next, We can use the Python SDK or CPP SDK to run the optimized model on GPU and enjoy the acceleration. Okay, we have introduced lots of OpenMMLab projects and we say that it is fancy, wonderful, and perfect. But what is the benefit of adopting it? Since some researchers may just write code from scratch PyTorch without any algorithm codebases. By adopting OpenMMLab, there are some significant advantages. The first one is its unified architecture. Users can learn once and use anywhere, since the architecture and APIs are almost the same for all OpenMMLab codebases. You can also implement once and use anywhere. For example, you can implement a backbone in MMPretrain and use it for object detection, segmentation, post-estimation with just modifying config files. Second one is unified benchmark. OpenMMLab provides fair baselines for academic research. For some research areas, different papers may adopt totally different settings, and we cannot conclude whether the model matters or the hyperparameter matters. In OpenMMLab projects, we investigate lots of training tricks and hyperparameters, and benchmark dozens of models under the same setting. This benchmark makes it easier to compare your work with others. Then the model design. OpenMMLab codebases are carefully designed based on research experience and engineering practices. Users only need to write a few modules instead of the whole pipeline, making it faster to develop and try new components. Lastly, we provide high-quality implementations. The efficiency and performance are usually higher than other ones, and the strict code style make it easier to read and maintain the project. Okay, that's all. In the next sessions, we will dive into more details of OpenMMLab. Thank you.